Many people know how to code a convolutional neural network, but not all of them really understand what's happening underneath those commands. For example, when you design a convolutional layer in Pytorch, how many filters do we have there? What are the dimensions of those filters? How many channels do those filters have? What do they really look like, really? Do those channels have equal values, or do they have different values? What about the linear layers? So in this video, we're going to answer all of these questions and really look deep into the model that we've designed in the previous video. So stick around. Hello everyone and welcome to ML Done. So in the previous video we saw how we can use Pytorch to design a convolutional neural network, yeah? And we saw how we could use the sequential method to have multiple layers of convolutions and tanh and average pooling all together wrapped up in one instance variable. In our class. And also we saw how we can design linear layers, and also, more importantly, we understood how those dimensions really get crushed all the way to the magic number 256 that we have in our source code of our convolutional neural network. So the math worked out, and that was good news. Now, what I really want to focus on today is to help you understand what those weights and filters in your convolutional and linear layers really look like, what about their dimensions and stuff. So without further ado, let's just get started. So we want to look into the parameters of our model. So just as a refresher, this is the model we have. We have two convolutional layers, we have two hyperbolic tangent layers, and we have two average pooling layers here, and we have a succession of linear layers here with nonlinearities. And in the forward pass, we've designed, we passed the input data through our CNN model instance variable, which contains all of our convolutional layers. And then we flatten it. I'm going to tell you what this line is, by the way, in this video. Then we use a succession of linear layers, fully connected layers, to crush the dimensionality of our x into all the way to only one value. Right? And then using the sigmoid function, we can decide whether this particular input image belongs to the tumor class or non-tumor class, right? So, so far, it's all clear and nothing new. Now, we want to get more comfortable with these layers, right? I want to tell you how you can use Pytorch to get access to these filters. So you have 6 filters here, right? We want to take a look at them. And when we claim that they have the dimensionality of 5 by 5, I want to prove that to you. So let's take a look how we can do this. First things first, in order to be able to, work with this class, we need to make an object of this class. So the name of this class is CNN, right? So let's create a model of this. So model CNN, right? So like creating object of any class really in Pytorch. That's exactly how it's done. Let's run this. Great. So now we have an object. If you want to take a look at your object, this is what your object looks like. So it has a CNN model with all the layers you've seen, and then it has an FC model with all the layers you've seen. And each of them is a sequential object of Pytorch. Now, let's see whether we can gain access to the CNN model, and then from there, whether we can gain access to this particular convolutional layer, right? So let's just go model dot, and if I press the tab key, it shows me everything that I can choose here. And the one that I'm interested in is in the CNN model, right? Now, if I printed this out, it only shows this chunk of our model, right? Because I want to show only CNN model. Now, what if I wanted to just look at the first convolutional layer? You notice these indices here, right? So using these indices, you can actually gain access to whatever layer you're interested in, really. So if I push, again, if I typed model.cnn, let me just create many cells here because we're gonna need them, right? So yeah, model.cnn. But over here, I'm interested in only the first element, which is only this layer, right? So if I just printed this bit out, there we go. So you only now looking at your first convolutional layer. Now, what if I want to take a look at the kernels or the filters inside? All I have to do is call the weight parameter here. So this weight has these kernels inside it, like all of them, right? So what are we expecting to see? Before I show you what's lying underneath, what you're expecting to see is that you will have a bunch of filters. How many? 6 of them, right? And each of them is gonna be a 5 by 5 tensor, right? But the question is, how many channels should each one of these 5 by 5 filters have? That's the first question. And the second question is, so for a given filter, if it has n number of channels, are those channels initialized equally and identically? Do they have equal values, or are they initialized differently, right? So let's just see what we're going to look at. Before I press run, remember our input data, those MRI images, they have 3 channels in them, right? Remember, so these filters, each filter has to be convolved with an input that has 3 channels, right? So let me just run this. There you go. So you get a bunch of tensors, like loads of values. It might be a little bit confusing to look at this whole thing all together. But one thing you can do is to literally take a look at the shape of this. First of all, let's just confirm the shape. If I run this, there you go. So we have 6 filters. Each of them is 5 by 5, and here it is. Each of them has 3 channels. Now that's interesting, isn't it? Because the input data has 3 channels. So if you want to have a filter, a weight filter that you want to convolve across all of your input image, right? And your input image has 3 channels. You need for your filter to have 3 channels. So you can imagine a small cube, right? That is going to move across a big cube that has 3 channels. And the first channel of that cube is going to be convolved with the first channel of your input data. And the second channel is going to be convolved with the second channel of your input data. And the third channel with the third channel of your input data, right? And then the result of all of that is going to be, again, an array with 3 channels. But remember, in Pytorch, and usually in all of those platforms, what they do later on is they sum up these 3 channels together, right? So every every filter with 3 channels is going to be convolved with your with your input data that has 3 channels, and the result of that is going to be a 2D tensor, right? So when you have 6 such filters, and you convolve each one of them by with your input data, you'll end up with 6 outputs, each of which is going to be 2-dimensional, right? So that is why we say that the output channel is going to be 6. That is why we're saying that that cube, that tensor that's going to be spit out all of this operation is going to have basically 6 channels, each of which is produced by your filters, right? By your convolutional filters, right? Now, so that is the whole story. Now, what I want to show you again here is that I want to take a look at these weights, right? So we have 6 filters, right? 6 filters. So I can look at the first filter here, for example, right? So this is my first filter, and I can even take a look at the shape of that filter. Remember, so before I run this, can you tell me what the shape of this filter is going to be? So remember, this is only one of our filters, right? So if I take a shape of that, so it has 3 channels, and each channel is a 5 by 5 tensor, right? And the other thing that you can see here, I can also show you this one. This is going to be interesting. So from the first filter, I'm going to take a look at maybe the first channel, right? So let's take a look at the first channel, right? So if I run this is going to be the output. So this is literally the first channel of this filter. And again, this is a 5 by 5 tensor, right? So this channel will be convolved with the first channel of your input data, say the RGB, whatever channel it is, right? And then the second channel is going to be convolved by the second input channel, and the third channel is going to be convolved with your third channel. And you notice that as I'm changing through these, the values are changing, right? So this means that Pytorch, when it creates a filter, a weight filter or kernel for your convolutional layers, because you're insisting that they have to have more than one channel, Pytorch initializes those channels for one given filter differently, right? So that was interesting, right? So this is how you can look into your, Pytorch weights and their shapes and their filters or whatever, right? So now you understand that this sort of hierarchical structure. The next thing that I want to talk to you about is the actual linear layer, right? So let's take a look at the linear layer. Let me just type this here, the linear layer, right? So demystifying the linear layer. So again, remember, our model, if I put a tab, if I want to gain access to the linear layers, remember that the linear layers in our model, we have designed them under the .fc model. So fc model instance variable, right? So if I just go back here, right, put fc model, great, right? So if I just print this, again, you notice that we're only getting the linear, the sequential object that has all of the linear and tanh layers, right? So again, similar to what I just showed you, it's exactly the same story. The first linear layer is gonna, we can access that like this, so the first element, and inside that you can take a look at the weights, right? Now, before I run this, so you notice that the in and out channels are 256 and 120, right? So if I type it, it shows you the actual values, but if I just take the shape of that, so you notice that it is a 120 by 256, basically swapped over here, and that's it, really. I mean, as simple as that. This is how you can gain access to the weights of your convolutional and linear layers. So that was easy, but the next thing that I want to show you, by the way, it is interesting because hopefully after we train and test these models, I want to show you how these weights change, right? So these are the learnable parameters of your model, right? All of these weights. So initially they're just initialized randomly. If you visualize them, you just get a noisy picture, right? But after the training is done, what you're expecting is to see some meaningful shapes in those filters, some patterns, hidden patterns, right? In the first convolutional layer, the second or the third, so the deeper you go, the more complex those filters would look like, right? So we will probably get back to this and we'll compare these filters for a dumb untrained model and for an actual smart trained model, right? So last thing I want to tell you about is that x.view command, right? So let me just put here. So I told you that this guy over here, you use it to flatten your tensor x, right? In order to understand what that really does, let me just create a random, simple tensor, right? So torch.tensor is how you create tensors in Pytorch, and you just have a sequence of values. And then if I run this, great. So this is a tensor now. So I'm going to reshape this. It is easy, right? So you can just say x equals x.reshape, right? And then you pass your desired shape in the form of a tuple, right? So let's just say 2 by 2 by 2 by 2, right? And I can run this. You can actually take a look at that x now, right? So 1, 2, 3, 4, 5, 6, 7, 8, all the way, right? And now I wanna get into this, right? So first things first, let's just understand what this x.size returns and what does that 0 mean, right? So if I type x.size, right? Okay, it literally turns the shape of that of our x, right? 2 by 2 by 2 by 2. Now, what if I wanted to only look at the first element? So it's just going to be this guy over here, right? So if I just type it, there we go. It's just 2, right? So what this does is this grabs the first dimension of your input data. Now, why does your input data have 4 dimensions? Because this is what it's going to be, right? When we start training our model, I'm going to show you that your input data is going to have 4-dimensional. Then you're going to say, wait a second. you've been telling us that our input data has a height and width of 128, and it has 3 channels. So you've been telling us so far that the input data is 128 by 128 by 3, right? So literally 3 elements. So what is this 4th element you're talking about? Well, the 4th element has nothing to do with the image itself, but it has something to do with the fact that when you train your neural network, you don't just pass images one by one to your neural network. You send them in batches or mini batches. So if you have 32 images in one batch and you send those images into your model, the shape that you're going to have in your X, so that X is going to be a batch of images, say MRI images, and then if you take a look at the shape of that particular batch of data, you will see 32. So the first element is going to be how many images we have in that batch, and then for example, you'll have the number of channels, and then you'll have 128 by 128. So this would be more or less, it might be the other way around, but that doesn't really matter at this point. So you get, the first one is going to be how many images we have in X, right? So this is the thing that we'll send into our model for training and for testing, right? So what this thing does is, so if the first value represents how many images we have there, then this guy over here it just grabs that first number. Basically, how many images do we have there? Each image is 128 by 128 and has 3 channels of such dimensions, right? So we have demystified this guy. Now what about x.view? What the hell is going on with this guy, right? Remember this, okay? This is very important, right? So basically what this guy is doing is it says that I have two data points, each of which has 2 channels, and each one of those channels is 2 by 2, right? So because you have 2 data points, this guy is going to play a very important role in understanding x.view, right? So if you take a look at, let me just bring x.view. So x.view -1, what this guy does is it flattens your n-dimensional, d by n by whatever the dimensionality of your x is. It literally grabs it and flattens it. So this is our x, right? It is 2 by 2 by 2 by 2. If you run this code, it literally just hammers it flat, right? But this is not what you want. Remember, you indeed have 2 input data there, right? So even though you pass this guy to your neural network, the neural network would grab each one of these input data separately and passes through itself, right? So the first input data goes in, and then the second input data goes in, right? So what you want is, you want to flatten, let me bring it here. So you want to flatten each input data independent of the other input data. So if you have 32 3 by 128 by 128 input data, you want to flatten each one of those input data separately, right? So you want to have 32 flattened arrays, right? Because each one is a different data point, right? So that is where this guy comes in, this guy, x.shape. What this says is, it says, look, Mr.view, in this x, we have this number of data points, right? I want you to flatten each one of them independently, right? So if in this case we have 2 data points, right? The first one is 1, 2, 3, so 2 data points, each of them is 2 by 2, right? In our example. So each of them, so the first one is 1, 2, 3, 4, a 2 by 2 array, and then the other one is 5, 6, 7, 8, right? So if you did this, it flattens this guy separately and then this guy separately, treats them as 2 different data points. Now if you run that, there we go, right? So you have this guy separate, comma, and then this guy separate. So if I take a look at the shape of that, you get again 2 data points, but this time each of them is gonna have 8 elements. Why? Because each of them is 2 by 2 by 2, and when you flatten an array that is 2 by 2 by 2, you'll end up with 8 flattened elements, right? So we use this command over here to literally, for every input data that has traveled through our CNN model, you flatten each one of them independently, right? And then you pass each one of those flattened input data through your FC model, through your linear model, and then you run sigmoid on each one of them independently. So each one of them will get crushed between 0 and 1, all of the elements in those flattened layers, and then you return the output. There we go. That's it, really. So yeah, I hope that this has been informative for you. So in this video, we understood what's really lying under all of these layers, what those weights look like, and what do the channels of those weights even look like. And we really understood what x.view really means and how it's really working behind the scene. So if you have any questions, feel free to post them in the comment section down below. I always appreciate it. And if you really enjoyed this video, feel free to like and subscribe to the channel, but more importantly, try to share the video so that more people could take benefit of this. Because I found this idea of understanding the logic underneath these layers to be not so much of a common knowledge, if you get me. So I think that's going to be beneficial to many people, and that's the goal of ML Done anyway. And also feel free to follow us on Twitter, LinkedIn, Instagram, Facebook, and whatever I've missed, I don't know. Also, we have a nice website, www.mldone.com, where we have very nice posts, informative posts actually. So yeah, until next time, take good care of yourselves. On behalf of ML Done, bye.